Hello, friends. It's a beautiful morning here. I hope you are doing well. IBM is here with another episode of Learning Physics, and today I would like to take this opportunity to introduce past paper questions on nuclear physics. Remember, this is Physics 9702 Cambridge Advanced Structured Questions, and specifically, this is going to be paper 4. This is part one of nuclear physics. Do not hesitate to subscribe. Make sure you click on you use the link and in the video description to download this document so that you can work in hard copy. It's easier to follow the lessons when you have a hard copy part of this document so that you can practice on that document to be able to excel in paper 4. Paper 4 will make magic, will change your grades. It has always done it for my students. So paper 4 will change your grades, will make your grades to go high. If only you can raise above 50% in that paper, your grade will always be good. So without wasting time, I just want to remind you that within this part of nuclear physics, we are going to explore a few things which may include mass defect, Einstein's mass energy relation. We shall talk about binding energy throughout the questions. We shall talk about nuclear fusion and nuclear fission. We shall talk about radioactivity. Those are the most important concepts that we shall be discussing in these past paper questions. The mass defect or the mass excess, Einstein's mass energy relation, that is E is equal to mc squared, binding energy, or we can even talk about binding energy per nucleon, nuclear fusion, nuclear fission, radioactivity, where we shall talk about half-life, decay constant, and so on and so forth. So these are some of the areas you must have discussed with your teachers or with your teacher in nuclear physics. And we want to try and explore the past paper questions in these areas. Without wasting time, let's go to the past paper document and start straight away. Okay, so nuclear physics, I called it unit 10 in this document, which you have downloaded or which you should download for easy understanding of the questions. I'll try to be so slow in this unit also because I want to write well so that some students don't listen, they prefer to see what is being written. So I'll try to write extremely well as much as I can to make the videos more clearer. So in some power stations, nuclear fission is used as a source of energy. We shall see what is fission, but fission is just splitting. The first question is saying state what is meant by nuclear fission. As a simple question answering technique, before you answer any question, look at the marks provided so that you can plan how much depth the examiner may be interested in. However, it is always good to write as much depth as you can after all. The more details you give, the more chances of including all the marking points which the examiner will be looking for. So what is meant by nuclear fission? Of course, I said fission is splitting. So nuclear fission is the splitting of a heavy nucleus into two lighter nuclei splitting of a heavy nucleus into two lighter nuclei. Of course, nucleus is singular, and since these are two, nuclei is plural. Into two lighter nuclei, lighter meaning their weight is smaller or their mass is smaller, into two lighter nuclei of approximately approximately the same mass Normally, the purpose of nuclear fusion is for the nucleus to gain stability. Therefore, it is going to have a higher binding energy per nucleon, approximately the same mass and higher binding energy. We shall see what binding energy is. Higher binding energy per nucleon. So that is nuclear fusion. The nuclear fission reaction produces neutrons. In the power station, the neutrons may be absorbed by rods. Normally, these are actually called boron rods. Complete the nuclear equation for the absorption of a single neutron. It is a single neutron by a boron nucleus with the emission of an alpha particle. So since it is a single neutron absorbed, so the boron nucleus absorbs a single neutron, and the neutron is N10. So we try to balance, of course, by emission of an alpha particle. So on this side we shall add alpha. An alpha particle is a helium nucleus. It is actually H4, not H3. So this will be He42. That is an alpha particle, or you can write alpha 42, which is accepted. So we try to balance the equation. You notice that the proton number is balanced. This side it is 3 plus 2, which is 5. This side is 5 plus 0, which is 5. But the nucleon number is not balanced. On the left, we have 10 plus 1, which is 11. On the right, we have 4. So we have to add 11 should be equal to x plus 4. So x is going to be 11 minus 4, which is 7. So the nucleon number here is actually 7. So that is the complete equation. Of course, if you're a chemistry student, you know that lithium is actually nucleon number is 7. Suggest why when neutrons are absorbed in the boron rods, the rods become hot as a result of this nuclear reaction. So the neutrons which are absorbed already have kinetic energy. They are actually moving. And since they are moving, they have kinetic energy. When they are absorbed by the boron rods, they are stopped by the boron rods, they are going to lose that kinetic energy. So the lost kinetic energy in the boron rods is what is converted into thermal energy. So we can simply say the emitted particles, or the neutrons have kinetic energy. The neutrons have kinetic energy. The neutrons have kinetic energy. When the neutrons are stopped, when the particles are stopped, they rapidly lose their energy. So when they are stopped, they lose kinetic energy in the rods. When when the neutrons are stopped, they lose their kinetic energy in the rods. The kinetic energy is the one which is converted. The kinetic energy of the neutrons is converted into thermal energy. Into thermal energy of the boron rods. Okay, so that is the neutrons. Of course, they have kinetic energy. So when they are absorbed or when they are stopped, they lose their kinetic energy rapidly in the rods. The kinetic energy of the neutrons is converted into thermal energy of the boron rods, or in the boron rods. The best correct English would have been in the boron rods. In the boron rods. The isotope phosphorus 33 undergoes beta decay to form sulfur, which is stable. Remember, whenever they don't tell you which beta particle, just know it is beta minus, which is stable. The half-life of phosphorus 33 is 24.8 days. Define half-life or radioactive half-life, whatever they call it. Of course, half-life is the time taken for the initial number of nuclei in a given sample to reduce to half, or to reduce to one half of its original value. The time taken for the activity of the sample to reduce to half its original value, that is half-life. So time taken for the initial number of nuclei, or I can call it activity of a sample. To reduce to one half of its original value. So that's what we call half-life. The time taken for the initial number of nuclei in a given sample to reduce to half of its original value. The time taken for the activity of a sample to reduce to half its original value. Show that the decay constant of phosphorus is 3.23 times 10 power negative 7 per second. Of course, we already know from our classes that decay constant is equal to ln of 2 divided by t a half. So this is going to be, that is divided by half-life. So this is going to be ln of 2 divided by the half-life. The half-life has been given as 24.8 days. So I will change it to, because we want the answer in per second, I will change the half-life into seconds. So this will be 24.8 days. Each day is 24 hours. Each hour is 3,600 seconds. So I press my calculator. So from my calculator, I can confirm that actually to three significant figures, the decay constant is 3.23 times 10 power negative 7 per second. Remember questions which require you to show that. Those questions, the examiner just checks the formula and the substitution. So don't forge anything to arrive at the answer. Make sure the method you are using is extremely correct, because it will still not give you a correct an answer. If you check that your method does not give you an answer, so it means you don't need to forge that it is equal to the answer. The answer itself carries no mark. A pure sample of phosphorus 33 has initial activity of 3.7 times 10 power 6 becquerels. Calculate the initial number of phosphorus 33 nuclei in the sample. So they have given us the initial activity, and we know from our classes activity is equal to decay constant times N naught. So this will be initial activity, N naught is equal to decay constant times N naught. So we want the initial number of nuclei, so N naught is going to be initial activity, which is 3.7 times 10 power 6 divided by the decay constant, we have got as 3.23 times 10 power negative 7. I check with my calculator. So from my calculator, I'm getting 1.15 times 10 power 13. You can also verify. Calculate the number of phosphorus 33 nuclei remaining in the sample after 30 days. Number of nuclei remaining after 30 days. So using the general equation, x is equal to x naught e power negative lambda t. Since we want the number of nuclei remaining, I will say n is equal to n naught e power negative lambda t. So I will just substitute here. N naught is 1.15 times 10 power 13 e power negative. Since we have time here in days and we were given the half-life in days, so I'll just write this as ln of 2 divided by 24.8 in days. That was the half-life. Remember, decay constant is ln of 2 over half-life. I've just maintained half-life in days. You can change it if you want, but me, I want to make the algebra simpler. Then times the time, which is 30 days. So decay constant is ln of 2 over 24.8 in days or per day. Then times 30 days. So the units of days have cancelled. So I will press my calculator here. So this is giving me 4.97 times 10 power 12. So it means the number of nuclei is 4.97 times 10 power 12. There's another simpler method. Another alternative. We know that the number of nuclei present is equal to half power n times n naught. So what is n? N is the number of half-lives, remember. So n is going to be equal to the number of half-lives, which is going to be 30. That is, remember, n is t over t a half. N is 30 over 24.8. So it means n, capital N, is going to be a half power 30 over 24.8, then times n naught, which n naught is, we got it as 1.15 times 10 power 13. So we can check this. So I'll just say 0.5 power in brackets I'll say 30 over 24.8. Then I multiply this by 1.15 exponent 13. I get the same answer. 4.97 times 10 power 12. Power 12. So the second method is always easier according to students, but I don't know which one is easier for you. As long as you're good at using your calculator, then it will be easy. After 30 days, the sample in B will contain phosphorus 33 and sulfur 33 nuclei. Remember, initially there was only phosphorus. It was only phosphorus, but they're saying after 30 days, there is now phosphorus 33 and sulfur 33 nuclei. In other words, remember there was initially only phosphorus. Now there is also sulfur. That means the amount of the number of nuclei of phosphorus must have reduced as sulfur was emitted. And how many sulfur nuclei were emitted? Remember, the number of phosphorus present after 30 days, we have got it as 4.97 times 10 power 12, but it was initially 1.15 times 10 power 13. So it was initially like this one, and now it is this. So what has been emitted must be sulfur. The number of nuclei which are present must be those of sulfur in the process of changing. So the number of nuclei of sulfur will be the difference between the original number of phosphorus and the current number of phosphorus after 30 days. So we want the ratio, number of phosphorus after 30 days over number of sulfur after 30 days. That is an easy question. So the ratio is going to be equal to number of phosphorus after 30 days is 4.97 times 10 power 12. Number of sulfur after 30 days is actually the original number of phosphorus, which was 1.15, minus the current number, this was times 10 power 13, minus the current number of phosphorus, which is 4.97 times 10 power 12. So it means phosphorus is emitting sulfur. The number of phosphorus nuclei which have disintegrated is equal to the number of phosphorus nuclei which are, sulfur nuclei which are present after 30 days. So we just subtract and divide from my calculator. So from my calculator, the ratio is 0.76. You can also verify. When a neutron is captured by a uranium-233 nucleus, the outcome may be represented by this nuclear equation. So we are saying that uranium-235 is capturing a neutron. It is giving MO plus LA plus X plus 7. For us, we don't need to know much of what these ones are. We just need to know the simplest ones like the neutron, the beta particles, and the helium nucleus, and the proton maybe. Use the equation to determine the value of X. So just try to balance. We check the proton number. Of course, I can't find X using the proton number because at the bottom of the neutron, this will be 0, so X will be useless. But I will use the nucleon number. So we have 235 plus 1, that is 236, should be equal to 95 on the right, plus 139 on the right, plus X, because we multiply X by this one here, so that will be X, then plus 7 times 0, that is 0. So what is X? Just take X, make X the subject, I'll just subtract 236 minus 95 minus 139, and I find my X as 2. So there are actually 2 neutrons being emitted. State the name of the particles represented by this one. Of course, these are beta particles or electron. That is a beta particle. Beta particle or the electron. Okay. Some data for the nuclei in the reaction are given in the figure. So they have given us mass in U, unified mass unit. Remember, 1U is 1.66 times 10 power negative 27 kilograms. So uranium was given molybdenum, lanthanum, proton, neutron. Of course, protons and neutrons do not have binding energies. We don't expect them to have binding energies, because binding energy involves separating nucleons. Now, a proton is a nucleon, a neutron is just a nucleon, so don't expect them again to be separated. Use data from the figure to determine the binding energy in U of a nucleus of uranium. So we want a nucleus of uranium. Since the proton and the neutron have no binding energy, we should just look for the mass of the separate nucleons. Uranium-235, 92. This one has 92 protons plus 143 neutrons. So we want to find the binding energy, the energy required to separate the nucleons, the 92 protons and the 143 neutrons. That is the binding energy. So we can find the mass of the nucleons, the mass of the separate nucleons. The mass of the separate nucleons is going to be equal to, now we have 92 protons, but each proton has a mass of 1.007 U, plus we have 143 neutrons, but each neutron has 1.009. So the unit here is U. I just press my calculator. So this is giving me the mass of separate nucleons to be 236.931 in unified atomic mass units. So the binding energy is the equivalence to the mass defect. So the binding energy, I'll write BE, is going to be the equivalence of the mass defect, and the mass difference is going to be 0.931, 236.931 minus 235.123. The mass difference in unified atomic mass units is the binding energy. From my calculator, I'm getting 1.808 in unified atomic mass units. Since they want the answer in U, I'll just leave it as 1.808 U. Show that the binding energy per nucleon. Normally we forget the per nucleon part. Of a nucleus of uranium-235 is 7.18 mega electron volts. Okay, so first of all, we can find the energy in joules. We can find that energy in joules. Remember, energy according to Einstein's equation, the energy equivalent to the mass defect is mc squared. So this is going to be, the mass defect is, we are going to just change that into joules. So this is going to be 1.80, let me call this one delta M, 08. change it to kilograms to be 1 times 1.66 times 10 power negative 27 times the speed of light 3 times 10 power 8, and this is squared. So this is now going to be the energy equivalent of the value we got above in joules. So I press my calculator here. So from my calculator, I have that this is 2.7 times 10 power negative 10 in joules. I want the answer in electron volts, and it is binding energy per nucleon. So the binding energy per nucleon is going to be 2.7 times 10 power negative 10 divided by, to change it to mega electron volts, I will divide by 1.6 times 10 power negative 13. Remember, 1 electron volt is 1.6 times 10 power negative 19. If it is mega, we multiply this by 10 power 6, so it becomes power negative 13. So that will be in mega electron volts, but we want binding energy per nucleon. So I again divide by the number of nucleons, which is 235. 235. So this is giving me 7.18 mega electron volts to 3 significant figures. The kinetic energy of the neutron before the reaction is negligible. Use data from B to calculate the total energy in mega electron volts released in this reaction. The kinetic energy of the neutron before the reaction is negligible. Use data from the figure to calculate the total energy in mega electron volts released in this reaction. So we can try to find out the energy which is not used in the reaction that has been given out. So going back to the table, we have that the binding energy per nucleon of MO is 8.09, and the mass difference was 94, but the nucleon number is 95. So this is the binding energy per nucleon. Total binding energy will be 8.09 times 95. Then the binding energy for LA, we are looking at on the left-hand side of the equation. LA, the binding energy per nucleon was this, and the nucleon number is this. So the binding energy alone will be the binding energy per nucleon times the nucleon number. Then on the right, we have calculated this as 7.18. This is binding energy per nucleon, but the nucleon number is 235. So if there is a difference, then the difference must be released, must be given out. So let's check that. Energy released is going to be the difference in the binding energies on both sides of the equation. Remember, on the left we have only uranium, which the other one has negligible kinetic energy. On the right we have MO and LA, the others have negligible kinetic energy. So the difference in the binding energies must be the energy that is released. So energy released is going to be on the right we have the binding energy per nucleon of MO was 8.09 times the nucleon number of MO, which was 95. So that is the total binding energy of MO. Then plus, on the right still, we have LA, which had binding energy as 7.92 times the nucleon number of LA, which is 139. So that is the total binding energy on the right. Then minus on the left, we have uranium binding energy. We calculated it as 7.18 times total number of nucleons. This was binding energy per nucleon times the number of nucleons, which is actually 235. So this is giving us the difference in energy is going to be the energy released. 8.09 times 95 plus 7.92 times 139 minus 7.18 times 235. So this is giving me 182.13. The unit here is going to be mega electron volts. So the energy released must be the difference in those two binding energies, and so this would be approximately 182 mega electron volts. Okay, so state what is meant by nuclear binding energy, or it is just binding energy. Is that amount of energy required to separate the nucleons, that is the protons and the neutrons of a nucleus, to infinity. Remember, infinity may not be a large distance, but at nuclear level, as long as the protons and neutrons and other particles which reside inside the nucleus, which are actually protons and neutrons alone, do not experience any force, then they are at infinity from each other. So that energy released, or that energy required, the energy required to separate the nucleons in a nucleus, or the nucleons of a nucleus, to infinity. That is the binding energy. It can be the energy released when the nucleons are brought from infinity to form back a stable nucleus. It is still binding energy. When I talk about nucleons, remember I'm talking about protons and neutrons. Those are the particles which reside inside the nucleus. The variation with the nucleon number A of the binding energy per nucleon Be is shown in the figure here. So we have binding energy per nucleon Be against the nucleon number. Okay. When uranium absorbs a slow-moving neutron, one possible reaction is uranium. We have already seen this reaction. Say the name of this type of nuclear reaction. Of course, when the reaction starts with absorbing a neutron, and you see that the resulting nuclei are of relatively lower mass, so that means it is fission. But since it starts with a neutron, then we can say it is induced by a neutron. Induced nuclear fission. It is induced nuclear fission. On the figure, mark the positions of the uranium-235 nucleus. Label this position U. And the molybdenum nucleus, label this MO. And lanthanum, label this La. So you look at the nucleon number. You see that uranium is 235. It must be extremely to the left, to the right. And MO has the smallest nucleon number. It should be the closest to the peak. La must be between MO and UA because of the nucleon number 139. So if I go back here, We know that here, close to the peak, we have iron that is close to the peak. We expect there to be iron Fe 56. It is very close to the peak. So it means uranium-235 must be almost at the end. So this will be U. U will be almost at the end because it's uranium-235. It has the highest nuclear number here. Then LA has 132, 39, and MO has 95. So it means MO must be closest to the peak than the rest because it has 95. So the MO is going to be around here. If this is 56, I think 95 can be around here. So I'll call this one MO. And then LA is 139. So 139 is closer. You just add 40 to around 44 to 95. So it means it is going to be somehow here. Let me say it's around here. So that is LA. So we have finished to label. Remember at the peak here you have iron 56, 26 because it's the most. Iron is the most is actually the most the one with the highest binding energy. So iron should be almost there. Okay. The masses of some particles and nuclei are given in the figure. So they've given us beta particle, neutron, proton, uranium, molybdenum, lanthanum. Calculate for this reaction the change in U of the rest mass. The change in U. Remember the equation? On the left we have uranium and the proton, then we have MOLA, 2 neutrons and the beta particle. Calculate for this reaction the change in U of the rest mass. So let's find the mass on the right hand side. The mass on the right hand side. So on the right hand side we have MO, we have LA, 2 neutrons, 7 beta particles. So we can't think of energy. So we have MO, which is 94.945 plus LA, which is 138.955 plus. There are 2 neutrons, so I'll say 2 times 1.009 plus. There are 7 beta particles, so I'll say plus 7 times 5.5 times 10 power negative 4. So I'm finding the total mass on the right hand side. So this is going to give us, it is actually 235.922 U. That is the mass on the right. So let's find the mass defect or the mass difference. The difference in mass or the change in mass in the rest of the rest mass is going to be equal to 35.922 minus 235. The rest mass of uranium is actually 235.123 plus. We have on the right we have we had a neutron, a single neutron, so it is plus 1.009. That is the total mass on the left hand side. So we subtract whatever answer you get. You don't mind about the negative, you are just getting the difference in mass. So the answer is always positive. So I'm subtracting. So the difference in mass is actually 0.210. So that is 0.210 to three significant figures. Then the energy released in mega electron volts to three significant figures. Energy released. So we are going to find the energy equivalent for this mass difference. And we know that energy is equal to the difference in mass times c squared. So this is going to be equal to the difference in mass is 0.210. We change it to kilograms, so that will be times 1.66 times 10 power negative 27 times the speed of light, which is 3 times 10 power 8, and this should be squared. Remember, we want the answer in mega electron volts. This one is in joules. This one is in joules. Okay, let me find it in joules. So this is 3.1374 times 10 power negative 11. Then I divide it by 1.6 times 10 power negative 13 to change it to mega electron volts. So 3.1374 divided by 1.6. So this is 1.96. I mean 196.1. So I'll just write 196 mega electron volts. Alternatively, you could, if you know what 1 U is equivalent to, then you can just, okay, you know that 1 U is equivalent to 934 mega electron volts. So if you have the energy equivalence, 0.210 U should be equal to 0.210 times 934, which is approximately 196 mega electron volts. Although I don't always encourage this, but if you know what 1U is approximately 934 mega electron volts. You can use it unless otherwise. One possible nuclear fission reaction is shown here. Barium and krypton are both beta emitters. Barium 141 has half-life of 18 minutes and a decay constant of 6.0 times 10 power negative 4 seconds. The half-life of krypton is 3.0 seconds. You see how small the half-life of barium is, so it is almost negligible compared to that of krypton. State what is meant by decay constant. What do we mean by decay constant? Remember, decay constant, we saw that the activity delta N by delta T was equal to negative lambda times N. And when lambda was the decay constant, so lambda was equal to dN by dt divided by N. The N is the number of nuclei which have decayed. N is the number of nuclei present. So the N over N is the sample space. N is the sample space, the N is the event. So event over sample space, that is probability. Then divide by T, so it is probability over time. So that is probability per time. So we can simply define decay constant as the probability of decay, of a nucleus, probability of decay of a nucleus in a sample per unit time. The probability of decay of a nucleus in a given sample per unit time, that is the decay constant. In fact, we can say, oh, it is the fraction of nuclei in a sample. The fraction of nuclei in a sample that decay per unit time. The fraction of nuclei in a sample that decay per unit time. A mass of 1.2 grams of uranium-235 undergoes this nuclear reaction in a very short time. That is a few nanoseconds. Calculate the number of barium nuclei that are present immediately after the reaction has been completed. Number of barium nuclei. So number of barium nuclei, we know that number of nuclei over Avogadro's number is the same as mass divided by the molar mass. So this implies that the number of nuclei I'm talking about here will be the mass, and the mass is 1.2 grams divided by the molar mass, which is uranium-235. The molar mass is 235 grams times Avogadro's number, which is 6.02 times 10 power 23. Avogadro's number is Na. I use the simplest relation, so Na. So what is N? So this is giving me 3.1 times 10 power 21. Use your answer in B, Roman 1, calculate the total activity of barium 141 and krypton 92, krypton 92, a time of 1.0 hours after the emission reaction has taken place. Let's go back to the question here, how it started. They say the half-life of barium is 18 minutes. The half-life of barium is 18 minutes. Yet the half-life of krypton is 3.0 seconds. So what does this imply? It implies that actually the activity of krypton is going to be negligible, because see how small its half-life is. So its activity is going to be extremely small, but you can still find it. Unfortunately, we don't even have the decay constant, because the examiner wanted us to be able to realize that the activity of krypton is too small to be neglected. Okay, so we want total activity of the barium and krypton. So we know that activity of krypton is negligible. The activity of krypton is going to be negligible. The activity of krypton is negligible because of its small half-life. The activity is negligible because of its small half-life. Let's now find the number of nuclei for barium. So for barium, we know that N is equal to N naught. e power negative lambda times T. So for barium, this is going to be N naught is going to be 3.1 times 10 power 21. E power decay constant has been given as 6.4 times 10 power negative 4. That is the decay constant. Remember, it is power negative, then times the time. Time is 1 hour. And 1 hour is 3,600 seconds. So that will be times 3,600. So the number of barium nuclei present after 1 hour is 3.1 times 10 power 20. Then we want the activity. So the activity, remember, is going to be equal to lambda times n. So this activity is going to be the K constant is 6.4 times 10 power negative 4 times number of nuclei present, which is 3.1 times 10 power 20. So this is giving me 2.0 times 10 power 17 becquerels. One likely means by which nuclear, remember this is going to be the total activity because the one of krypton is negligible. Otherwise, if it was not negligible, then we would add it to the one of barium to find total activity. But since it is negligible, the only activity will be that of barium. One likely means by which nuclear fusion may be achieved on a practical scale is the DT reaction, that is deuterium-tritium reaction. State what is meant by nuclear fusion. So fusion is combining, fission is splitting, but all of them result into a higher binding energy per nucleon. So the combining of two lighter nuclei to form a heavier nucleus with a higher binding energy per nucleon. So combining of two lighter nuclei come together to form a relatively heavier nucleus, just one, with a higher binding energy per nucleon. And it will, of course, the one which is formed is always more stable. That is nuclear fusion. In the DT reaction, a deuterium nucleus fuses with a tritium nucleus to form a helium nucleus. The nuclear equation for this reaction is shown here. Some data for this reaction are also given, as we can see here. Calculate the energy in mega electron volts equivalent to 1 U. What energy is equivalent to 1 U? In other words, we want the energy equivalent of 1 U. That is a question, it is very common. So energy, according to Einstein's equation, is given by the mass defect times c squared. The mass here is 1 U. So we shall say this is 1.00 times 1.66 times 10 power negative 27 to change it to kilograms. Then times 3 times 10 power 8, and this is squared. So this gives me So this gives me 1.494 times 10 power negative 10 in joules. We want it in mega electron volts, so we divide 1.494 times 10 power negative 10 divided by 1.60 times 10 power negative 13. So this makes this to be 934. Let me check. So it is actually supposed to be 933.75, which is approximately 934 to three significant figures, or sometimes it is 930 to two significant figures. Use data for the figure 9.1 and you answer in Roman 1, so we shall be using 934 to determine the energy released in this DT reaction. So first of all we need is the mass defect in U. So we need the mass difference. We shall need the mass difference. Let's look at the equation. On the left, we have deuterium and tritium. So the total mass, we shall add the masses of these two on the left. So deuterium is 2.01356 plus tritium, which is 3.01551. That is total mass on the left. On the right, we have helium and a neutron. So we are finding total mass on the left, on the right. So we have 4.00151 plus the other one is 1.00867. So plus 1.00867. That is total mass on the other side. So we are trying to find the difference in the masses. So I am getting the difference in mass as 0.01889 in unified atomic mass units. But they said we should use our answer in Roman 1 to determine the energy. So the energy equivalent is simply going to be 0.01889 times, since 1 U is 934 mega electron volts, so I'll just multiply this by 934 to get the answer in mega electron volts. 0.01889 times 934. So this is 17.65, or approximately 17.7. Approximately 17.7 or 17.6, depending on how you rounded off earlier on. So that is 17.7 or 17.6 mega electron volts. Okay. Suggest why, for the DT reaction to take place, the temperature of the deuterium and tritium must be high. We know that deuterium is positively charged, tritium is positively charged. Bringing them together requires a lot of energy because they must be repelling each other. So that is very easy. High temperature means that they have high kinetic energy. So therefore they can easily fuse for the reaction to occur. So high temperature means high kinetic energy. High kinetic energy of the nuclei. So it means the nuclei of DT nuclei, the DT nuclei will now have high kinetic energy, that is at high temperature. So deuterium, so D and T nuclei can overcome the electrostatic force of repulsion or the electrostatic repulsion. They can overcome electrostatic repulsion between them and collide. So at high temperature, they can easily come together for the reaction to occur. Because at high temperature, it means they have high kinetic energy, which is therefore able to overcome the force of repulsion between them for the reaction to occur. Okay. Radon 222 is a radioactive element having half-life of 3.82 days. Radon, when found in atmospheric air, can present a health hazard. Safety measures should be taken when the activity of radon exceeds 200 becquerels per cubic meter of air. So it should not exceed 200 becquerels per cubic meters of air. Define radioactive decay. I think now we know that radioactive decay constant, that is the probability of decay of a nucleus per unit time. Probability, the probability of decay of a nucleus in a given sample per unit what? Per unit time. The probability of decay of a nucleus in a sample per unit time, that is decay constant. The probability that a nucleus will decay in a given sample per unit time, that is the decay constant, or the fraction of the nuclei decaying per unit time. Show that the decay constant is given by that. So at this point, we now know that decay constant is ln of 2 over T1/2. So this is going to be equal to ln of 2 over the half-life, which is given as 3. The half-life is 3.82 days. So it will be 3.82 days. But remember, a day is 24 hours. And an hour is 3,600 seconds because we want the answer in per second. So here we just press our calculator. So this is going to be equal to 2.1 times 10 power negative 6 per second. A volume of 1.0 meters cubed of atmospheric air contains 2.5 times 10 power 25 molecules. Calculate the ratio number of air molecules in 1.0 meters cubed of atmospheric air over number of radon atoms in 1.0 meters cubed of atmospheric air. They have already told us from the above that actually radon 22 when found in atmospheric air can present a health hazard. Safety measures should be taken when the activity of radon 222 exceeds 200 becquerels per cubic meter of air. So the activity is 200 becquerels per cubic meter of air. So let's find the number of radon nuclei in 1 cubic meter of air. That should not be exceeded. So we know that activity is equal to lambda times n. So the number of nuclei is going to be the activity, which is 200, divided by the decay constant, which we have seen as 2.1 times 10 power 6. Power negative 6. So this is giving me this is going to be 9.5 times 10 power 7. So this is the number of radon nuclei which should be in 1 meter cubed. When it exceeds this, then it means safety precautions must be taken. So calculate the ratio, number of air molecules in 1 meter cubed, which has been given as this one, over number of radon atoms in 1 meter cubed of atmospheric the air for the minimum activity of radon at which safety measures should be taken. Remember, the minimum activity was 200 becquerels per meter cubed. So we can now find our ratio. So the ratio is going to be 2.5 times 10 power 25 divided by 9.5 times 10 power 7. For my calculator. So from my calculator, the ratio is 2.6 times 10 power 17. During the decommissioning of a nuclear reactor, a mass of 2.5 times 10 power 6 kilograms of steel is found to be contaminated with radioactive nickel 6328. The total activity of steel due to nickel contamination is 1.7 times 10 power 14 becquerels. Calculate the activity per unit mass. So this is activity per that is activity. So we will need activity per unit mass. So this was total activity. So activity per unit mass. So this is going to be equal to activity per unit mass, that is over mass, is going to be equal to 1.7 times 10 power 14 divided by the mass, which mass is 2.5 times 10 power 6. Just press our calculator here. So from my calculator, you can also verify I'm getting 6.87. 6.8 times 10 power 7 becquerels per kilogram. So that is the activity for 1 kilogram of steel. Special storage precautions need to be taken when the activity per unit mass due to contamination exceeds 400 becquerels per kilogram. So the activity should not exceed 400 becquerels per kilogram. If it does, then special precautions should be taken. So this is going to be the minimum activity, but we are seeing the activity per unit mass of steel is 6.8 times 10 power 7 becquerels per kilogram. Nickel 63 is a beta emitter with half-life of 92 years. The maximum energy of unemitted beta particle is 0.067 mega electron volts. Use your answer in A to calculate the energy in joules released per second in a mass of 1.0 kilograms of steel due to the radioactive decay of the nickel. Use your answer in A. In A, we got the activity of steel per kilogram. The activity per kilogram. So how much energy is actually released? So 1 kilogram, of course, when we say the activity is 6.8 times 10 power 7 becquerels per kilogram, we mean that 1 kilogram is going to release 6.8 times 10 power 7 nuclei or particles per second. That's what it means. So we are saying 1 kilogram of steel. This is just a simple analysis for people to see. So 1 kilogram of steel, according to the activity, 1 kilogram of steel emits 6.8 times 10 power 7 particles per second. That's what we mean by that activity of 6.8 times 10 power 7 becquerels per kilogram. It means in 1 kilogram of steel, we expect 6.8 times 10 power 7 particles emitted per second. But remember, the energy released by each particle emitted is 0.067 mega electron volts. So the energy released per second in 1 kilogram the energy released per second in 1 kilogram of steel is going to be, since each particle is going to release energy of 0.067 mega electron volts, and yet there are 6.8 times 10 power 7 particles emitted per second in 1 kilogram times 0.067. Since we want the answer in joules, I'll change this times 1.6 times 10 power negative 13. This is changing it from mega electron volts to joules. So I press my calculator here. So this is 7.3 times 10 power negative 7 in joules. Use your answer in Roman 1 to suggest, with a reason, whether the steel will be at a high temperature. You see the energy involved here, 7.3 times 10 power negative 7, is a very small amount of energy. It is a very small amount of energy, and therefore we really don't expect that the steel will be at a very high temperature. So I will simply say 7.3 times 10 power negative 7 joules is a very small quantity. It's a very small quantity of energy. So steel will not be warm. Because the energy is very small, the steel will not be at a high temperature. Use your answer in A to determine the time interval before special storage precautions for steel are not required. Remember, the activity should not exceed 400 becquerels. The activity should not exceed 400 becquerels. When the activity reaches 400 becquerels, then it means special precautions should now be taken. But remember, the initial total activity is 6.8 times 10 power 7 becquerels. So let's check. So activity, according to the general equation, activity is equal to A naught e power negative lambda times T. And of course, we know that decay constant is equal to ln of 2 over T a half, or over half-life. So I'm now substituting. Activity should not exceed 400. That should be the activity present. The initial activity is 6.8 times 10 power 7 becquerels per kilogram, e power negative, so this would be lambda 2 ln of 2 over T a half, which is 92, and this is times the time which I want to find. So I just divide both sides and I introduce ln. So when I introduce ln this side, I will have ln of 400 divided by 6.8 times 10 power 7. The other side I only remain with the power, that is negative ln of 2 over 92 times t. So I will divide both sides. So ln 400 divided by 6.8 exponent 7, ln of the answer divided by ln of 2 over 92. So I'm getting T as 1,600 years. I have to check this again. 400 divided by 6 point exponent 7 times 92 divided by negative ln of 2. Yes. So this is approximately 1,600. Time in years can always be rounded off to two significant figures. This is 1,598.5 years, which is approximately 1,600 years. There's another simpler method or shortcut. Activity is equal to, this is another method. Activity is equal to a half power n times the original activity. All we need is to find n. So a half power n is equal to a activity at that time is going to be 400 divided by the activity, the original activity, which is 6.8 times 10 power 7. So we introduce ln to find n. So I'm going to introduce ln to find n. So that means n is equal to the ln of this value divided by ln of 0.5. So what is n? I'm introducing ln both sides. Okay, so this will be ln of 400 over 6.8 times 10 power 7 divide by ln of 0.5. So what is n? So n is 17.4. N is 17.4, but remember n was the number of half-lives, and number of half-lives is the time over t a half. So I want t, so t will be n times the half-life. So I multiply n times the half-life, which is 92 years, and I get the same thing. So t is going to be n times the half-life, and n is 17.4 times the half-life, which is 92, which gives you almost the same answer, approximately 1,600 years. That is another method that you can think about. Distinguish for an atom between a nucleus and a nucleon. Of course, a nucleus is the small central part or the core of the atom. The nucleus is the small central part of an atom, which is the core of the atom. It's the core of an atom. That is the nucleus. Then a nucleon. I've been saying a nucleon are those particles which reside inside the nucleus. These are the protons or a neutron contained within a nucleus. The proton or a neutron contained within I think within is one word. Contained within a nucleus. So the particles which reside inside the nucleus are the ones we call the nucleons. Those are the protons and the neutrons. Radon gas is a naturally occurring radioactive gas with half-life of 3.8 days. The activity of radon gas in a room is found to be 97 becquerels in each 1.0 meters cubed of air. Calculate the decay constant in per second. So we know that decay constant is the probability of decay per time. So this is ln of 2 over half-life. So this will be ln of 2, and the half-life is 3.8 days. We want the answer in per second, so we shall convert. So this will be 3.8. 1 day is 24 hours, and 1 hour is 3,600 seconds. So from my calculation, I'm getting this as 2.1 times 10 power negative 6 per second. The number of radon atoms are giving rise to an activity of 97 becquerels. Okay, so we know that activity is equal to the decay constant times the number of nuclei. So the activity is 97, decay constant is 2.1 times 10 power negative 6, then times n. So I just press the calculator to find n, dividing both sides. So I'm finding that n is equal to 4.6 times 10 power 7. So that is 4.6 times 10 power 7 A volume of 2.5 times 10 power negative 2 meters cubed of air in the room contains 1 mole of molecules. 1 mole. Remember, 1 mole is 6.02 times 10 power 23 molecules. 1 mole is 6.0, that is actually Avogadro's number. So, and this is contained in 2.5 times 10 power negative 2 meters cubed of air. Determine the ratio for 1 meter cubed. So it means we now have that 2.5 times 10 power negative 2 meters cubed contains 1 mole of molecules, and 1 mole is 6.02 times 10 power 23 molecules. So it means 1 meter cubed contains 6.02 times 10 power 23 divided by 2.5 times 10 power negative 2 molecules. Okay, so find the ratio for 1 meter cubed of air, the number of radon atoms over the number of air molecules. So now we now know the number of air molecules in 1 meter cubed, and the number of radon atoms. Since this was the activity for each 1 meter cubed of air, so this what we have got above is the number of radon atoms in 1 meter cubed of air. So the ratio is going to be equal to 4.6 times 10 power 7. That's the number of radon atoms in 1 meter cubed over this number of over what we have got here. So I'll just get the reciprocal. So this will be divided by 6.02 times 10 power 23 times 2.5 times 10 power negative 2. I have just divided by the expression here, the number of molecules in 1 meter cubed of air. So I'm pressing my calculator. So this is giving me 1.9 times 10 power negative 18. 1.9 times 10 power negative 18, that is the ratio. State what is meant by the binding energy of a nucleus. We have already seen what binding energy is. The energy required to separate the nucleons in a nucleus to infinity or completely. So that is the binding energy. So the energy required to separate the nucleons of a nucleus or in a nucleus to infinity. You note that when I talk about infinity, I said the particles do not experience any force due to each other. So it means they are infinitely far away from each other. By the way, it can also be the energy required when the energy released when nucleons combine from infinity to form a nucleus. It can also be the energy released when nucleons combine from infinity to form a nucleus. So that energy which is released. So when they come together, the energy is released. To move them apart, energy is required. So that is a nuclear binding energy. Data for isotopes of uranium are given in the table here. So what is meant by an isotope? What is meant by an isotope? So when we talk about an isotope, isotopes are nuclei having the same proton number but different number of neutrons, therefore different nucleon number. So state what is meant by isotopes. These are nuclei. Nuclei having the same number of protons but with different numbers of neutrons. Different numbers of neutrons. So that is, those are isotopes. Then complete the figure 9.1. So the first column, this column is for binding energy per nucleon, and the other one is binding energy in mega electron volts. So here we just multiply binding energy per nucleon by the nucleon number. So this is going to be 7.59 times the nucleon number, which is 235. 7.59 times 235. So this is going to be 1784 to 4 significant figures. Then this one is going to be, we are going to divide by the nucleon number. So that will be 1802 divided by nucleon number is 238. 1802 divided by 238. So since this is the 3 significant figures, so this will be 7.57. Okay. Uranium-235 has half-life of 7.1 times 10 power 8 years. Show that the decay constant lambda of uranium is given as that. So that is easy. We now know that decay constant is equal to ln of 2 divided by half-life divided by t1/2. So this is going to be equal to ln of 2 divided by half-life, which is 7.1 times 10 power 8. They want the answer in per second. We shall change years to seconds. 1 year is 365 days. Each day is 24 hours. Each hour is 3,600 seconds. So I press my calculator to check. So from my calculator, this is 3.1 times 10 power negative 17 per second. A sample of uranium has activity 5.0 times 10 power 3 becquerels. Calculate the mass of the sample. So that is the activity. We want the mass. Remember, we said mass over molar mass is the same as, we said mass over the molar mass is the same as number of nuclei over Avogadro's number. So we want M. We need N. We know Avogadro's number. We only know the molar mass, but we don't know N. So we need N from activity equals to lambda times N. We know that the activity is given as 5 times 10 power 3. The decay constant, we have calculated it above. It is actually 3.1 times 10 power negative 17, then times n. What is n? I just divide both sides to find n. So I'm getting n as 1.61 times 10 power 20. That is n. So I can now go back and substitute in this formula here and find the mass. So the mass is going to be n, which is 1.61 times 10 power 20, divided by Avogadro's number, which is 6.02 times 10 power 23, times the molar mass, which is 235 in grams. Remember, I've not changed this. This is still in grams. So I have 1.61 times 10 power 20 divided by 6.02 exponent 23 times 235. So this is giving me 0.063 in grams. The isotope radium-224 and radium-226 both undergo spontaneous alpha particle decay. The energy of the alpha particles emitted from radium is 5.6. So 224 emits 5.68 and 226 emits 4.78. So you notice that the energy of the alpha particle emitted by radium-224 is higher than the energy emitted from an alpha particle of 4.78. What does that imply? The one which emits a particle with more energy, it means it is actually going to be it was actually more or less stable. That's why it emitted a particle which has more energy. There was a high chance of it to undergo disintegration than the one which emits a particle of less energy. So part A, state what is meant by the decay constant of a radioactive nucleus. So we now know that decay constant is the probability of decay. Probability of decay of a nucleus per unit time. That is decay constant. Suggest with a reason which of the two isotopes has the larger decay constant. In other words, which one had a higher probability of decay? I say the one which emits a particle that has more energy was extremely less stable. In other words, had a high chance of it decaying. It had a high chance of it decaying. In other words, it required less amount of energy for it to decay. That's why it gave out a particle that has more energy. The one which emits a particle with less energy, it means most of the energy was needed for it to split or for it to decay. So it means it was extremely more stable. Therefore, we can simply see that radium-224 has a greater decay constant. So it is radium-224 with a greater decay constant. The reason or the explanation is very simple. Its alpha particle has greater energy. Meaning that the parent nucleus was less stable. Its alpha particle has greater energy, meaning that the parent nucleus was less stable. In other words, needed less energy to disintegrate. And more likely to decay. Because the parent nucleus was less stable, then it was more likely to decay, hence a higher decay constant. Hence having a higher decay constant. So it is radium-224. Its alpha particle has greater energy, which means that the parent nucleus or radium-224 was less stable. And if it was less stable, it is more likely going to decay. It has the more chances of decaying. And remember, decay constant is the probability of decay. So since it has a higher chance of decaying, then it has a higher decay constant. Radium-224 has a half-life of 3.6 days. Calculate the decay constant of radium-224, stating the unit in which it is measured. So we now know that decay constant, lambda, is equal to ln of 2 over T1/2, which is going to be equal to ln of 2 over the half-life, which is 3.6, and this is so this is 0.193. Maybe to take you back to this equation here, a nucleus which is less stable, it means energy, if most of the energy is added in decaying, a lot of energy is going to be given to the product. In other words, more excess energy is given to the products. So a less stable nucleus uses less energy in its disintegration, and more of the excess energy is given to the products. A more stable nucleus uses more energy in its disintegration, so less energy remains to be given to the products. That's why you see for radium-224, there was 5.68 mega electron volts given to alpha, yet for 226 it was 4.78. So it means there was more excess energy given to the alpha particle for radium-224, which means less was used in disintegration than that used in 226. So this one is going to be per day. When I write 0.9193, that will be per day. Alternatively, you could also find that in per second. I will just write this as 0.193 per day. Determine the activity of a sample of radium-224 of mass 2.24. So activity, remember, is going to be lambda times n. But n over number of Avogadro's number is the same as mass over the molar mass. So n is going to be the mass, which is 2.24 milligrams. So mil is times 10 power negative 3 in grams, divided by the molar mass, 224 grams, times Avogadro's number, 6.02 times 10 power 23. I just made n the subject here. And since these ones cancel, I think this will be 6.02 times 10 power grams has cancelled. Let me check here. So from my calculator, this is times 10 power 18. But that's not the answer here. So activity is lambda times n. So the activity is going to be lambda, which lambda is 0.193. Because I want the answer in becquerels, by all means I will need the decay constant in seconds. Let me check method 2. Decay constant is ln of 2 divided by 3.6 times 24 times 3600. So this is 2.23 times 10 power negative 6 per second. Since in part 1 they didn't specify which unit, of course you could have both any of the two answers, but in part 2 you need the one in the per second. So this would be 2.23 times 10 power negative 6 per second. That is the K constant times n. We have got n as 6.02 times 10 power 18. So this is 1.3 times 10 power 13 becquerels. The variation with the nucleon number A of the binding energy per nucleon Be of nuclei is shown here. On the figure, mark with the approximate positions of iron. Of course, iron is at the peak. That one has no question. So this is going to be iron Fe at the peak. Then zirconium Zr, that is 97. That must be on the right of the peak, 97, because nucleon number is increasing to the right. So 97 could be somewhere here. So that is Zr. We know uranium is on the extreme end. Then H21, of course, H21 is the first particle, the first nucleus on this, because it has two nucleons. So H21 is going to be at the extreme bottom here. It is the first particle here. So that is H. We can't have H1 because H1 is a single proton, so there's nothing like splitting it. Binding energy does not apply. Binding energy does not apply to H1, a single proton. Set what is meant by nuclear fission. Remember we said fission is splitting. So splitting of a heavy nucleus. Splitting of a heavy nucleus into two. Splitting of a heavy nucleus into two lighter nuclei. Remember, nuclei is a plural. And these are normally of approximately the same mass. And they actually have higher binding energy per nucleon. So approximately of the same mass. Two lighter nuclei of approximately and higher binding energy per nucleon. So the splitting of a heavy nucleus into two lighter nuclei of approximately equal mass and higher binding energy per nucleon, that is what we call the nuclear fission. By reference to the figure, explain how fission is energetically possible. How is fission energetically possible? How is fission energetically possible? Okay, so fission must be only energetically possible if the binding energy of maybe the parent nucleus is less than the sum of the binding energies of the fragments. That is, if the binding energy of the parent is not less, then fission is not going to be possible, because fission involves splitting of one nucleus to give us two nuclei which have a higher binding energy per nucleon. Remember, here they gave us binding energy per nucleon, and the binding energy of a nucleus is going to be binding energy per nucleon times the nucleon number. So we are saying binding energy of a nucleus binding energy of a nucleus is supposed to be equal to, from the graph, to be binding energy per nucleon times the nucleon number. Binding energy of a parent nucleus is less than the sum of the binding energies of fragments for fusion to occur. Binding energy of the parent nucleus is less than the sum of binding energies of the I will call them fragments. Binding energy of the fragments, so fission can occur. So let us assume that actually maybe Zr breaks down to give us iron and H. So the binding energy of Zr must be less than the total binding energy of iron and H for fusion to occur. If it is not less, then fission cannot occur. Remember, it is the nuclei on the left-hand side of the peak, on the right-hand side of the peak, which undergo fission. Fission is only possible if the binding energy of Zr is less, because Zr is going to be the parent here. Should be less than total binding energy of Fe and H. If they are equal, then fission cannot occur. If the total binding energy of Fe and H is less than that of Zr, still fission cannot occur. So the reaction is energetically possible because the binding energy of the parent nucleus is less than the sum of the binding energies of the fragments, so fission can occur. State what is meant by the binding energy of a nucleus. So we now know what binding energy is. The energy required to separate the nucleons in a nucleus to infinity. So that is the binding energy of a nucleus. The energy required to separate the nucleons of a nucleus to infinity. Remember, I said the nucleons, those are the protons and the neutrons. Show that the energy equivalence of 1.0 U is 930 mega electron volts. This is an easy equation. Energy is equal to mass defect times C squared. And remember, 1 U is 1.66 times 10 power negative 27. So the energy is going to be 1.66 times 10 power negative 27 times the speed of light, 3 times 10 power 8, and this is squared. So when I press my calculator, so this gives me 1.494 times 10 power negative 10 in joules, which is going to be 1.494 times 10 power negative 10 divided by, I want it in a mega electron volts. So I divide by 1.6 times 10 power negative 13. And this gives me 933.7, which is approximately 930 mega electron volts to two significant figures. Data for the mass of some particles and nuclei are given in the table. Use data from the figure and information from B to determine in mega electron volts the binding energy of deuterium. So binding energy, we need the mass difference. We want the answer in mega electron volts, and we have already verified that 1 U is 930 mega electron volts. So without wasting time, we shall just use that relationship. So the mass difference is going to be equal to, we are finding for deuterium H21. So the mass of the deuterium nucleus, we expect that the total mass on one side should be greater. So I will say, let me assume it is greater on, it has one proton and one neutron. Let me say the mass of the nucleons is greater. So this would be H21 has one proton and one neutron. So one proton, that is 1.0073, plus one neutron, that is 1.0087, minus the mass of the stable nucleus, 2.0141. Answer. So this gives us 1.9 times 10 power negative 3 in U. So the binding energy is simply, since 1 U is 930, so this will be 1.9 times 10 power negative 3 times 930. And this gives us 1.8. The binding energy per nucleon, that is easy, of zirconium. So we first of all find the mass defect. So zirconium has 40 protons and 57 neutrons. So this one has 40 protons and 57 neutrons. So the mass difference is going to be 57 times the mass of one neutron, which is 1.0087, then plus 40 protons, that is 40 times the mass of one proton, 1.0073, then minus the mass of a stable nucleus. And the mass of the stable nucleus is 97.0980. So that is minus 97.0980. So from my calculator, the difference here is 0.69 in unified atomic mass units. We want to remember binding energy per nucleon. Of course, binding energy here would be 0.69, and 1U is 930, so this would be times 930. To find per nucleon, we divide by the nucleon number of zirconium, which is 97. So this is 6.61. Okay, state what is meant by the decay constant. So we now know that decay constant is the probability of decay per unit time. Probability of decay of a nucleus per unit time. The probability of decay of a nucleus per unit time, that is the decay constant. Show that the decay constant lambda and the half-life T1/2 of an isotope are related by that expression. So that is very easy. At half-life, when T equals to T1/2, we know that the number of nuclei present reduces to half of the original. So this will be N0 over 2. Let's say N0 is the origin. And remember the equation, N is equal to N0 e power negative lambda T. We are substituting the above conditions. So N will be N0 over 2 being equal to N0 e power negative decay constant, and the T is T1/2. So N0 has cancelled, we remain with a half equaling to e power negative lambda times T1/2. So we introduce ln. So we have ln over half equaling to, when you introduce ln to the right, you only remain with the power, so that will be negative lambda times T1/2. And ln over half is the same as negative ln of 2, or negative 0.693. So this is negative 0.693, which is equal to negative lambda times T1/2. So we have just concluded that lambda times T1/2 is equal to 0.693 because the negative cancels. That is an easy question. Those 3 marks are free. In order to determine the half-life of a sample of radioactive isotope, a student measures the count rate near the sample as illustrated here. Okay. Initially, the measured count rate is 538 per minute. After a time of 8 hours, the measured count rate is 228 per minute. Use data to estimate the half-life of the isotope. So we know that activity is equal to the incident initial activity e power negative lambda times T. So after some time, the activity is 228. Initially, it was 538. So this will be e power negative decay constant. With decay constant is lambda. The time is 8 hours. So this will be times 8. So I introduce ln. So this will be ln of 228 divided by 538 is equal to negative lambda times 8. So what is lambda? So lambda here is 0.107 per hour. That is lambda. And remember, half-life is equal to ln, decay constant is ln of 2 over half-life. So the half-life is going to also be ln of 2 divided by the decay constant divided by 0.107. Ln of 2 divided by 0.107, which is giving us 6.478 hours. So this is approximately 6.5. So that is 6.5 hours. We could also find this from by finding n. We know that activity is equal to a half power n. This is another alternative times a naught. So it means a over a naught is going to be 228 over 5. That 8 is equal to a half power n. We introduce ln. So we have that ln of a half times n is equal to ln of 228 over 538. So I'm trying to find n. So I'll just divide ln of 228 over 538 divide by ln of 0.5. So I'm finding n as 1.239. But remember, n is equal to t over t a half. N is t over t a half, and I want half-life. So half-life is going to be t over n. So t a half is going to be time, which is 8 hours, over n, which is 1.239. So I'm just going to say 8 divided by the answer, and I still get approximately the same thing. I still get this as 6.5. You can verify. So this is another method which my students believe it is the best. So one thing we need to note is that normally when the answer is to be quoted in hours, always try to write it in two significant figures only. Two significant figures. The accepted value of the half-life of the isotope in B is 5.8 hours. That is the accepted value. But we have got 6.5. The difference between this value for the half-life and that calculated in B cannot be explained by reference to faulty equipment. So the equipment is not faulty. Suggest two possible reasons for this difference. Number one, we notice that actually the accepted value is less than the calculated value or the actual value. So this is simply because of, number one, the random nature of decay. Remember, radioactivity is both random and spontaneous. Random in that we cannot predict which nucleus in a given sample will decay next. So that is the random nature. So it means we could have underestimated the actual value, the expected value, compared to what is really observed. Number two, we can talk about background radiation. Radiations in the surrounding could also affect or increase the count rate. They could increase the count rate or affect the half-life. And number three, the daughter products could also be radioactive. If the daughter product is also radioactive, then this is going to increase the activity. And therefore, it will be higher than expected. Those are some of the possible reasons which are causing the difference in the half-life or the difference in the activity. The element strontium has at least 16 isotopes. One of these isotopes is strontium-89. This isotope has half-life of 52 days. State what is meant by isotopes. So we have said isotopes, these are nuclei having the same number of protons, but different numbers of neutrons. Different numbers of neutrons. Those are isotopes. Same number of protons, but different numbers of neutrons. Calculate the probability per second. That is decay constant, of course, of a nucleus of strontium. So probability of decay per times decay constant. The probability of decay per unit time is equal to the decay constant, and we know that decay constant is ln of 2 divided by t1/2, and this is going to be ln of 2 divided by half-life is 52 days. We want the answer in per second. So this will be 52 times 24 hours times 3600. And this is giving me a 1.54 times 10 power negative 7 per second. The laboratory prepares strontium-89 source. The activity of the source is measured 21 days after preparation of the source and is found to be 7.4 times 10 power 6. That is after 21 days. Determine for the strontium-89 source at the time that it was prepared the activity. So activity is equal to A naught e power negative lambda t. After 21 days, the activity has been given as 7.4 times 10 power 6. So we want the initial activity. So 7.4 times 10 power 6 is equal to the original activity e power negative. The decay constant is 1.54 times 10 power negative 7. Then times the time is 21 days. So I will say 21 times 24 hours times 3600. That is the time in seconds. So I am just going to divide by e power that to get A naught. E power negative 1.54 exponent negative 7 times 21 times 24 times 3600. Divide both sides by that value. So I'm getting A naught as 9.8 times 10 power 6 as the initial activity. 9.8 times 10 power 6. But like I said, there's another simpler method. Which is activity present is equal to a half power n times the original activity A naught. We have A, we can just find n. We know n is the number of half-lives, which is t over t1/2. The time is 21 days. The half-life is 52 days. So this is 21 over 52 days. So I just substitute. A naught is going to be equal to A, which is 7.4 times 10 power 6 divided by a half power N, which N is 21 over 52. So that is an easy mathematics. So I have that 7.4 exponent 6 divided by, open brackets, 0.5 power 0.5 power, or divide by 0.5 power, I'll open the bracket, 21 over 52. Get used to your calculator, and this is still giving me A naught as 9.790 times 10 power 136 power 6, which is approximately 9.8 times 10 power 6. So this is another alternative. That is another alternative method that you can check out. Then we want the mass of strontium 89. We want the mass of strontium 89. So remember, we know that mass over molar mass is equal to the number of nuclei present over Avogadro's number. We just don't have n. So we can find n from activity is equal to lambda times n. So n is equal to the activity, which is 9.8 times 10 power 6 divided by, remember we are looking for the, this was the initial activity. So we want to find the mass when it was prepared. So the mass is going to be, n is going to be 9.8 times 10 power 6 over the decay constant, which we found as 1.54 times 10 power negative 7, that is n. Now let's find the mass. So the mass is going to be 9.8 times 10 power 6 divided by 1.54 times 10 power negative 7, that is n. Then divide by Avogadro's number times 6.02 times 10 power 23. I'm just substituting that formula, times the molar mass. It is 89. So I will change it to, because we want the answer in grams, I will just leave it as 89. So this will be times 89 in grams. So I'm pressing my calculator here to check. So this gives me a 9.4 times 10 power negative 9 grams. State what is meant by nuclear fusion, by a nuclear fusion reaction. Remember, fusion, two lighter nuclei come together. So two light nuclei, not light this light electromagnetic radiation, but light in terms of weight. Two lighter, or let me say lighter nuclei combine to form a heavier nucleus. Form a heavier nucleus with a higher binding energy per nucleon. So that is nuclear fusion. I said whether it is a fission or fusion, the binding energy is always going to be higher, and because the formed nucleus must be more stable. One nuclear reaction that takes place in the core of the sun is represented by that equation. A deuterium nucleus is combining with hydrogen to form helium-3, 2. Calculate the energy in joules released in this reaction. So we notice that on the left we have deuterium and hydrogen. We need the mass difference. The difference in mass is going to be whatever side you start with, there is no problem. I can start with the left. Whether you get a negative, you just know it is a difference in mass. So this side we have 2.01410 plus 1.00728. That is the total mass on the left, minus on the right, which is 3.01605. I get the difference here. So the difference is 5.33 times 10 power negative 3 in unified atomic mass units. Then we can find the energy equivalent. Remember, energy is going to be delta M times C squared. So this is going to be 5.33 times 10 power negative 3. We change this to kilograms, so that is times 1.66 times 10 power negative 27. Then I change this, times the speed of light, 3 times 10 power 8. This is squared. So this gives me 8.0 times 10 power negative 13. The temperature in the core of the sun is approximately 1.6 times 10 power 7 Kelvin. That's way high. Suggest why such a high temperature is necessary for this reaction to take place. Of course, we know that deuterium and hydrogen are both positively charged nuclei, so for them to come together, they should be overcoming the force of repulsion. Therefore, high temperature means high kinetic energy. The kinetic energy of the proton and deuterium must be very large so that the nuclei overcome the electrostatic repulsion between them. So high temperature means high kinetic energy. So kinetic energy of the kinetic energy of the proton and deuterium must be very large. Must be very large so that the nuclei overcome the electrostatic repulsion between them. Yeah, so the kinetic energy must be extremely high in order to overcome the electrostatic repulsion between the deuterium and the proton nuclei so that fusion can now occur for the reaction to take place. Yeah, I think part 1 should stop here. And we meet in part 2. Thank you, and I hope you have enjoyed this video. I hope it has been helpful. Meet you in part 2.